Yeah, given a heap with 77 nodes, are 77 nodes equal to 7 elements? Yeah, that's correct. Or equal to, yeah, all right. All right, let me explain this question. Yeah, pretty simple. Answer 77 nodes corresponds to 77 elements. All right, yeah, 77 elements. Yeah, we know index 0 cannot be used for a node. All right. Yeah. Index 0, we cannot use it to store a node, but if you want to use it to store other information, that's okay, but just not for node. So we do not treat index 0 element as a node. Okay, yeah. So then we use indices. Use indices from 1 through 77, okay, for nodes. Yeah, so that's the understanding. Yeah, root, yeah, given a heap, yeah. So here we assume max heap, right? Yeah, because we assume max heap, okay, yeah. If we assume max heap, the root must be the max element and at the position 1. Yeah. So that's the basic information. Yeah. How many leaves with the longest path? Yeah. So remember, in the nodes, I drew a diagram, right? So here to remind you a little bit, yeah, the situation, it corresponds to this case. Yeah. Suppose we have this case. All right, let me draw. All right, leaf. Yeah. Look at all the leaves for this case. Yeah. These are the leaf nodes. Leaf nodes with longest path. With the longest path. All right, so look at this path. Longest. How many edges? Those 3 edges. How do we count the number? Now, the length. We count the number of edges. Another path with 3 edges. Yeah. Here, 2 longest path. All right? Yeah. Do not count these leaves. Yeah, okay. Yeah. Hope you know how to count. How to count. You know, like that. Okay. All right. 77. Yeah. Yeah. 77. Definitely, you do not need to draw all 77 nodes. Yeah, but you just draw some, you know, a few levels. Yeah. All right. So that is this question. Yeah. If further question, you just ask. Yeah. If you feel it's enough to understand, yeah. If you feel not enough, you can keep asking. All right. Yeah. Next one. Question 19, 20, 24. We have several choices to combine. All right, two numbers. Yeah, merge. For question 19, number one, we can combine 10 with 15, then combine with 25 elements. Two, we can combine 10 with 25, then combine with 15. Yeah, three, 15 with 25, then at the last, we need to find the minimum number of the above three options. Yeah, that's correct. Yes, that's correct. Okay. If yes, do question number 2024 have the similar logic? All right, yeah. So let me answer this question. Question number 19, number 20, yeah. Question number 19 and number 20, they are similar, yeah, because we have three ordered arrays. Yeah, so we handle them in a similar way. Yeah. The only difference is the formula is different. Yeah. Question 19, the best case, we use the minimum of m and n formula. Question number 20, the worst case, we use the formula m plus n minus 1 when we merge two ordered arrays. Yeah. So for your question, we treat, using the same logic to solve these two questions. Yeah. But for question 24, situation is different. The question 24, four ordered arrays, right? Yeah, four ordered arrays. Then the number of possibility much bigger, right? Think about that. The number of possibility, because if you want to exhaust all the cases, how many cases? Think about that. Okay. Yeah. So, you just imagine a little bit. That could be a large number, right? Yeah, that could be a large number. Yeah. That means to go through all the possible cases, too much work. Okay, yeah. In order to reduce, so here, in order to reduce the number of cases, we can apply one strategy, yeah, one special strategy. Okay. We can apply the greedy strategy. Yeah, greedy strategy. So we have one simple way we can do the merge, but the problem is the greedy strategy may not give the best solution. Yeah. May not give the best solution. We don't know. Yeah. Yeah, we don't know. Yeah. But for this question, if you apply greedy strategy, I treat it as acceptable. All right. I'll treat it as acceptable. Okay, yeah. Because in this case, if you want to do better, you find the best solution, yeah, that is quite challenging. So here, all right. So the best solution, let me describe the best solution here. Okay, the best solution. You'll find it and prove it. Prove that it is the best. Yeah, definitely this is the best thing we like to have. Yeah, but to get that, probably too challenging. All right, yeah, too challenging. So I do not require it. I do not require it. Okay, yeah. For some of the students, if you really like to solve challenging questions, you can try. Okay, you can try this direction. Okay, for me, you know, if you just use the greedy strategy to solve this one, I treat as acceptable. Okay, I treat it as the close to optimal solution. Yeah, even if it's not optimal, I treat it as close to optimal. So I feel it's good enough. Okay, good enough for ordinary students. Okay, yeah. For some students, you really want to, you know, challenge yourself. Yeah, you can try to find the best solution. But for, you know, most of the students, just find near optimal. That's fine, near optimal. All right, let me talk about the greedy strategy. Here, let us list the sizes of these four arrays in order: 10, 15, 22, and 37. Okay, the ascending order. Yeah. All right. Then when we do the merge, yeah, we merge two ordered arrays with two smallest sizes, 10 and 15 first. Okay, after the merge, the size becomes 25, right? Yeah, the size becomes 25. Then can we reorder the remaining three ordered arrays? This time 22 becomes the first, 25 becomes the second, and the 37, okay, in ascending order like that. Then apply greedy strategy another time. We merge two ordered arrays with two smallest sizes. These two, the combined size 47, right? Yeah, 47. Okay, yeah. But the last round, only two ordered array, 37 and 47. We just merged them. Okay, yeah. Yeah. Each step, because for the worst case, right? Worst case, each step, you apply the formula m plus n minus 1. When you do the merge, apply this formula. Yeah. So that's the greedy strategy that could give us near optimal. Yeah, here I treat it as near optimal solution. Yeah, and it is good enough for most of us. Okay, so that's my answer. Okay, and this way, it is simple enough. Okay, you do not need to do too much work. Okay, yeah. All right, so that's these three questions. So I'll answer them together. Yeah, next one, NAMI. Yeah. Yeah, okay. So even the question overlap. Let me see if you have different angle. Okay. Yeah. So don't worry, even you ask question that we answered before, I just look at if there is a different angle in your question. Okay. All right. Nami's question number 19, if compare 10 element array with 25 element, does that mean now have 35 element array? Or can you then compare 10 array with, right? Yeah. If you compare 10 element array, 25 array, you need to complete the whole processing, right? Whole merge operation. Whole merge operation, you will get 35 element. Then you cannot use that 10 element another time. All right? You already use it. Use it up. All right? Yeah, 35. Then the 20, then the 10 element array is gone. After you complete the merge, you only have 135 element ordered array. That old 10 element array is gone. So you cannot merge that 10 element array and the 15 element array another time. You messed up. In that way, you messed up. All right? Yeah. So after so here, each array, you can only use that array data for your merge operation only once. Okay, yeah. So that's your first question. Second, number 25, is the heap limited to the structure explained homework 2 hints video? Yes, right. Can the left child value be smaller than the right child for max heap? Yes. Yes. All right. Yeah. Let me answer question number 25. Yeah. All right. Okay. Yeah. All right. Yeah. In this way. Yeah. All right. First, when we define parent node, left child node, right child node. Okay, yeah. So for that left child value, all right. So left child, left child value could be smaller. Yeah. Could, yeah, here. Could be smaller than right child value. Okay, yeah. It's legal, right? It's legal. Yeah. So when you draw that tree, yeah. So you have more cases. You allow left child value smaller than right child value. Yeah. So you need to cover all the possible cases. Okay. Yeah. If any of you, if you ask me to, to go to a little more details, let me know. Yeah. Basically follow the hint video. Yeah. Our homework number 2, the hint video. Yeah. So I give you a lot of information on this question. Yeah. So if any of you need me explain a little more, you can let me know. Okay. All right. Next question. What is meant that an asymptotic notation belongs to? All right. Yeah. Okay. Yeah. So that wording thing, belong to. Yeah. Because I think you're talking about a few questions belong to, right? Yeah. All right. Yeah. Yeah, here, yeah, this question, number 4. All right. So here, asymptotic notation. First, the meaning of asymptotic notation. Now, each one, this notation, it means a set of functions. Okay, each asymptotic notation represents a set of functions. Okay, yeah, so you can treat it as, set. Then functions in the set follow some special conditions. Yeah. All right. Now we use the word belong to. That means an element belong to a set. Right? Yeah. An element belongs to a set. Okay. So that wording. Yeah. Which of the following asymptotic does the best case efficiency of quicksort? First, we need to know the best case efficiency for quicksort. What is that function? Yeah. Okay. Or we need to know the the growth function. The growth function for the best case efficiency of the quicksort. Yeah. There must be one function, right? Yeah, based on our notes, there must be one special function you can find. Okay. Yeah. Yeah. Let's say f of n. Okay. F of n. Yeah. Then, based on your knowledge about the asymptotic notations, there you can see which of the 5 options does it belong to. Okay. Yeah. Because this function we treat it as an element. This function we treat it as an element. Okay. This element, yeah, we want to see it belongs to which of the, which of the 5 sets. Yeah. All right. Yeah, but there is another case. Yeah. An element, yeah, let's say X belongs to A and an element belongs to B. It could be both, right? Yeah. There is a possibility an element could belong to both. If it belongs to both, then pick the smaller set. Pick the smaller one. Smaller one as the answer. Okay? Yeah. Yeah, because there must be one set that is smaller. All right? Yeah. The reason is this is a better answer. If you pick the smaller set, that is a better answer. Yeah. because you give the better answer. All right. Yeah. When you have more than one answers, pick the best one, best answer. Okay. Yeah. The smaller set corresponds to the better answer. Okay. Yeah. For this question. Okay. All right. Yeah. So that's my answer for this question. Next one. Question number 25. Is it possible that the left child value is greater? Yeah, yes, it's possible. Greater or even equal, okay? Yeah, equal. Greater, equal, less, yeah, no restriction, okay? Yeah. I thought the max heap that we only need to consider that the parent node value is greater than yeah, that's correct. Yeah. Our condition, our max heap condition, we only require that the value of the parent node greater or equal. Yeah, actually we include the equal case. Yeah, equal is allowed. Okay. Yeah. So let me, yeah, because since two students asked this question, so let me elaborate it a little more. Yeah, this question, elaborate it a little more. Okay, yeah. For a max heap. Okay, yeah. We only require, all right, more precisely, more precisely, yeah. So the value of P greater or equal, I include that equal case. So if you see the value of a parent equals one of the values of its child node, no violation. Do not treat it as a violation. Val of left child and the value of P greater or equal to the value of its right child. Okay, yeah. Why we include the equal case? Yeah. Think about, we want to use our heap structure to cover all the cases, including an array with duplicate elements. Okay, yeah. Usually when we consider an array of data, we do not require distinct elements. Okay, we do not require distinct elements. But in our discussion, many times we say we consider distinct elements. That's for, for ease of discussion. Now, we want to make our discussion easier. Now, and our assumption, our assumption can be extended to cover duplicate elements easily. Okay, so we don't worry about that. We don't worry about that extension, further extension. So we make that convenient assumption. Okay, all right. But in general, when we do sorting, we allow elements with duplicate values. Okay, yeah. In that situation, the equal case acceptable. Equal case acceptable. Okay, yeah. No violation. We do not treat it as violation. Yeah. So that's more precise way. All right. Yeah. Nami again. So max C can have L greater or equal to L. Or yeah, that's correct. Yeah. So when we compare values from R and L, three possible cases: greater, less, equal. Three possible cases, no violation. Okay. No matter which one happens, no violation with respect to the max heap property. Okay, yeah, so that's the understanding. Yeah, all right, yeah, okay, yeah, good, yeah. So any more questions? Yeah, try to ask questions, yeah, as many as possible. All right, yeah. Okay. Here, because there is no new question, yeah, I may like to talk about project overflow, because one student asked me overflow. So let me explain that part. When I do the explanation, if you have new questions, you just type in the chat area. So when I see your questions, I will answer. After I explain the overflow problem, then I will answer. All right. Yeah. So anytime, yeah, because you need to prepare. Sometimes you need to prepare yourself, which question to ask. Yeah. When you are ready, you type your question. So then I will answer. All right. Here I see a new question, number 22 from Carmack. Yeah, let me see. What's that question? Oh, yeah. Median. All right, good. All right, let me explain this question. For question 22, when the term median is used, does this mean median as in it is the middle, right? Correct. Middle of the array physically, yeah, after the array is sorted, yeah. Or is its value value in the middle? All right, not position. Yeah. All right. So let me clarify. Cormac's question. Yeah. The median. Yeah. Median. Let me clarify. So when we have an array, yeah, we can look at two different factors. All right. Yeah. One factor positions, another values. All right. So for the Cormac question, he asked me if we mean in the middle of the values or in the middle of the position. All right. So the answer is middle of the values. Yeah. Middle of the values. That means, all right, because the position, when you do the sorting, you change the positions, right? Now, when you do sorting, you change the positions. Yeah. But you never change the values, right? Yeah. You can change positions, but the values of the elements cannot be changed when you move elements around. Yeah. So, but the positions only after you sort the array so you can use the positions. Okay, yeah. So if you want to use middle of the positions, you need to assume that you sort the array. After you sort the array, then you can use the middle position for the median. Yeah. But if you look at the middle of the values, you do not need to sort, right? Yeah. You know the meaning of the middle of the value. So you do not need to sort. Okay. So here to clarify, yeah, because so many students ask me this question. Yeah. So I clarify in this way. Yeah. With respect to which factor, position factor or value factor. If you're talking about the value factor, then middle of the value, it is always correct to describe the median. All right. But if in case, sometimes you like to use the position factor, you have to sort the array. Then you can talk about the middle of the position. Otherwise, it's wrong. Okay. For the original array, then if you use the middle of the position, that's the wrong description for the median element. Okay, that's the clarification for this question. Okay, all right. Next question. By first partition. Yeah, all right. Yeah, first partition. We know quicksort, we need to do partition operations, many rounds, right? Many rounds. Yeah. So then in question, yeah, so here you talk about question number 12. Yeah, all right. Question number 12, it's a given array. Yeah, all right. So this is the given array, and we know, here I ask you to do, apply one partition step. Yeah. So here, I do not ask you to sort it. Yeah. I do not ask you to sort this array. Yeah. Because to sort this array, we need to apply the partition operation several times recursively. Okay. Yeah. Not too much work. Yeah. So I do not ask you to do all the work. Okay. Because if you can show me you can do one partition operation, then I treat you, you know how to do partition, so you can do whole quicksort. Yeah. So here you only need to show me the result after the first partition step. The first. Okay. Yeah. So in the in my notes, I show you the diagram. Yeah. So we pick the last element as the pivot element. Yeah. So then we scan all the elements from left to right and do comparisons. Yeah. And what kind of swap operation we need to do. Yeah. At the end, you need to put the pivot element in place, okay, to complete the whole partitioning. Okay, we know the pivot element is 5. All right, yeah. So at the end, what I expect, yeah, the result, expect, okay, some element, certain number of elements. Okay, all right. Then 5, right? Yeah, because at the end, you need to put that pivot element in place. And, yeah. Okay, these elements less than 5, these elements greater than 5. Okay, yeah. but the order of these elements should come from your partition step implementation. Okay, not by your observation. Yeah, some students, yeah, you know, when I did grading before, some students, they didn't really do the formal partition step. They just, you know, arrange elements by eyes, by observation. Okay, that's not good. That's not right. Okay, because I need to check if you really understand the partition details. Okay, yeah. So you need to follow our partition procedure. Okay, yeah. So this question is designed to check that understanding. Yeah, because that step is critical for quicksort. So if you understand this step, then I treat you as, you know, understanding the whole quicksort. Okay, the whole quicksort. Yeah, yeah, fine. Yeah, you get it. Yeah. All right. Yeah. And I could pivot doesn't change. Yeah. Pivot doesn't change. Pivot doesn't change. If you say the pivot value doesn't change, doesn't change. Yeah, but yeah, we need to, the last step, we need to do one swap operation to put the pivot element in place. Put the pivot in place. We need that step, because after that we can do recursion. Okay, so I like you complete the last step, put the pivot. Yeah, because your question, if you do not put the pivot value does not change, no value is changed. All right, when we do sorting, we only change the positions. We cannot change the value, any value we cannot change. Okay, yeah, because in that way you change your data, you change your original data. We don't want to change original data. We just rearrange original data. So we can change their positions, but we cannot change their any value, any of the values we cannot change. Yeah. Yeah. So if you say we do not change the pivot value, yeah, that's correct, because you cannot change any of the values. Okay. Yeah. But we need to move to the, you know, right position. Yeah. In that way, you can keep going. You can continue the conquer step, divide and conquer. Okay. Conquer by further recursions. Okay. Yeah. Yeah. All right. Yeah. So keep asking your questions. Yeah. Before you give me new questions, yeah, let me jump to that overflow case. Yeah. Because I think this student, last time, although I talked about the implementation steps, but when one student implemented, this student got something a little different. You know, the behavior of the overflow slightly different from our discussion. Yeah. So I did experiment by myself. So I explained that my experiment result. Yeah. So when you write your own code, so you can, you know, do in the right way. So here, let me talk about my experiment a little bit. Yeah. Okay. Yeah. All right. Yeah. So yeah. So you for other students, you just keep type your questions in the chat area. After I finish Yeah, let me use 10 minutes to, yeah. Yeah, let me use 5. Yeah, I hope. Yeah, I don't know. Yeah, try to make short. Yeah, yeah. All right. For the overflow, remember, we can consider two cases. One, signed long integer, another unsigned long. All right, yeah. Here, I only ask you do one of the cases. You do not need to do both. All right, do one of the two cases. Okay, yeah. Yeah, based on our project description, you remember two methods. One use math formula, another use the, detection. Yeah, use the value comparisons detection. Yeah, so you choose either signed, long, integer. Yeah, because you need to consider positive, negative. Okay, yeah, unsigned, only 0 and positive. All right, the answer will be different. Yeah, here, so when I do the experiment, so in Java, so here I use Java. Okay, yeah, C++ could be different. Yeah, so in Java, for signed case, we can declare long type, long primitive data type, long, that means signed long. Then for unsigned long, there is no unsigned long type. Okay, yeah, yeah. I try very hard. I search. So although there is this concept, unsigned long concept, but it's very complicated. Yeah. So we need to, use, some of the solutions gave me using the third-party library. Okay. Yeah. So I don't like to use the third-party library. Okay. Yeah. So later for unsigned case, so if some of you like to use unsigned case, yeah, later I find a easier solution, use Java big integer. Big integer, we know there is no size limit, okay? But big integer, there is a method called, bit length, bits length or bit length, whatever, yeah. But there is another method called bit count or bits count. Okay, when I tested bit count, it doesn't work. Okay, when I use bit length, it works well. All right, yeah, bit length, we know for 8 byte. Yeah, so if it is greater than the bit length greater than 64 bits, then we get an overflow. Okay, yeah. If not greater than 64, then no overflow. So we use this way. We can do detection. Yeah. All right. For signed case detection, I found we need to check the negative value for overflow. For overflow, okay, negative value. Yeah, because that way, yeah, last time I talked about one way, it doesn't work. So that student told me it doesn't work. I check it myself, doesn't work. You know, use C minus A checking not equal to B. Yeah, because the experiment result tell us even there is an overflow, B minus A still equals, C minus A still equals B. Okay, so this method couldn't detect it. Yeah, couldn't detect it for signed case. For signed case. Okay, yeah. So that's why we need to check, you know, for example, if C less than 0, then there is overflow. Okay, yeah. Else, yeah, fine. Okay, yeah, yeah. No overflow, yeah. So this is the detection way. Okay, yeah. Just let you know, yeah. All right, yeah. Let me show you my experiment result a little bit, yeah, so you can get an idea. Yeah. So let me bring up my Eclipse. Yeah. All right. Let me show you this is my experiment result. Okay. Yeah. The first part, I print out all the Fibonacci numbers. Yeah. All right. Yeah. One by one, each line corresponds to one Fibonacci number. All right. So you can see at the point when I equals 91, because I start from index 0. When I reaches 91, C, you see the negative number, right? Negative 62 something, right? That's the overflow happens. Yeah, overflow. Yeah. And because this I equals 91, if we convert it to the Fibonacci number size, yeah. So here, look at the size. How do we figure out the size? Yeah. When I equals 0, our C corresponds to Fibonacci number of 2, F2. Okay, so here you can see the valid Fibonacci number, the size equals I plus 2. Valid Fibonacci number size corresponds to I index plus 2, 0 plus 2. So C corresponds to F of 2. All right, then let's figure out the valid Fibonacci number size. Yeah, because when I equals 91, an overflow occurs. So that means this line cannot be accepted. Okay, so we need to go back to the previous line when I equals 90. This previous line, I equals 90, that's the valid line. The Fibonacci number corresponds to this line is a good one, yeah. But the size corresponds to I plus 2. So 90 plus 2, 92. Yeah. So we can output the maximum good size for the Fibonacci number using the signed long data type 92. Okay, yeah, based on the experiment. Then I use big integer, then I check the number of bits. Okay, yeah, 1, 2, 3, you know, yeah. When I find the number of bits greater than 64, that's the overflow, greater than 64. for unsigned integer. Now, I can use all 64 bits, but 65 bits then overflow. Yeah. So this I equals 92 line hits the overflow. So we need to drop it. So we need to go back to I equals 91. But I equal to 91, its corresponding good Fibonacci number size, I plus 2, so it's 93. It's 93. 91 plus 2, 93. That gives us the largest possible Fibonacci number that can be represented by 64 bits unsigned long integer. Okay, yeah, that's the experiment result. All right, yeah, I only have 10 minutes. Let me go back to question number 11. Emily asked me, yeah. For other students, you just check if you have more questions. Yeah. All right, yeah, so this question. Multiple choice. Which of the following statements about the quicksort is correct? All right, yeah. A, the quicksort gets the best case efficiency for both ascending order array and a descending order array. Yeah. So here we consider ascending order array, descending order array, and we also look at the best case and the worst case. Yeah. Here the question. Yeah. So here I give you the general principle for quicksort. Yeah. You know, the general description for the quicksort. Okay, yeah. For the quicksort, we know we use divide and conquer. Okay, yeah. Divide and conquer, yeah. So here, when we look at the best case and the worst case, best case, worst case. Okay, all right. Best case happens when data distribution is balanced. Data distribution is balanced. Okay, yeah. So that means when you do one partition, you use the pivot element to do partition. You have left subarray, right subarray. The left subarray and the right subarray, they have almost equal sizes. Yeah. The size difference is very small. Okay, so then we treat so that data distribution is balanced for partition operation. Okay, yeah, for partitioning. Yeah, but if yeah, so that is yeah. So let me write it separately. Yeah, so that's the best case. Yeah. Worst case, the data distribution is unbalanced. Unbalanced. Okay. What's the meaning of unbalanced? Okay, all right. When you do partition step, yeah, so this suppose this is the pivot P. Yeah, the left subarray very small, the right subarray, you know, very big. The size difference is big, or the other way around. Okay, the pivot element is here. Yeah, right subarray very small, the left subarray, you know, very large. The difference of the sizes is big. That's the unbalanced case. So the worst case corresponds to the unbalanced case. Okay, all right. Now let us move to the ascending order, descending order. Can you use the, yeah, ascending order is like that, right? Ascending order. Descending order like that, okay? Yeah. When you use ascending order, the last element as the pivot, right? Is the pivot, this pivot would cause the unbalanced distribution or balanced distribution. For this case, descending order, you use last element as the pivot. Is this pivot would cause the unbalanced distribution or balanced distribution? Then you can get the answer, okay? Yeah. Look from that view. Data distribution, balanced or not, with respect to the pivot element for ascending order array or descending order array. Yeah, okay. I hope it's clear enough. Yeah, look, yeah, in that way. Li's question number 2. Question number 2. All right. Is it possible that one can solve the selection problem by an algorithm in bigger or bigger? Yeah. The conclusion is in our notes. Yeah. Because this one we call the linear algorithm. Linear. Why linear? Because we represent your constant C times n. This is a linear function. Okay. Constant C multiplied by n. Yeah. And in our class, I didn't give you the solution because the solution is too complicated. Okay. The solution is too complicated. But I gave you the solution. I gave you the conclusion. Yeah. I said, in my conclusion, look at, so if I say there is a linear algorithm or not, or I may use other words, if there is a big O of n solution or not for the selection problem. Okay? Yeah. So you needed that part to answer this question. Yeah. That part. Yeah. Another, yeah. So here the question. Yeah. The answer yes or no, it relies on if there is a linear algorithm for selection problem or not. Okay? Yeah. Yeah. So in our notes, in the textbook, so even you search on web, you can find the answers. Okay? You can find the answers from different places. Yeah. Our notes, the textbook, or search the web, because this conclusion is a famous one. Okay? Yeah, it is a well-known, it's a important conclusion, result. It's a linear solution for selection problem. It's an important result. So you can find it easily. Yeah, you can find the answer easily. Okay, yeah. All right, yeah. Any other questions? Yeah, so we do not have much time left. Yeah. I hope so you feel better